Welcome to the lecture number 24. The last few lectures what we are discussing is the fluorescence quenching, and we have seen basically few things. Let me list it out. Dynamic quenching, I also have seen static quenching, I have seen combined static and dynamic quenching. I also have seen that apparent static quenching, this is because of the quencher is near to the fluorophore, right. And now what I will try to tell you is another type of quenching, which is called the fractional quenching. Let us say I have two such kind of fluorophore in a molecule, and the proteins are one of the typical example for such kind of fractional quenching. So, let us say I have this protein over here, I have just drawn my protein like this way, looks good. I have one fluorophore which is present here and one fluorophore which is present over here. What I can comment about the position of these two fluorophore? This fluorophore is easily reached by the quencher, but this is not. This is present in buried location. Okay. So, this is accessible and this is not accessible. If so, now if I add quencher, so quencher will come and interact with this fluorophore, but quencher cannot come and interact with this fluorophore. So, the fluorescence intensity due to this fluorophore will decrease, this fluorophore will decrease, fluorescence intensity of this fluorophore will decrease, but fluorescence intensity of this fluorophore will be unaffected, right. Fluorescence intensity of this fluorophore will be unaffected. Clear? Now, let me write this as site A because it is accessible. So, this is site A, and let me write this as my site B because this is in the buried. Without addition of quencher, when there is no quencher, then the total fluorescence intensity I 0 can be written as I 0 for A position of the A and plus I 0 of B. I can simply write that one. Now, as I argued that when you will add the quencher will quench the fluorescence of A, but it will not going to quench the fluorescence of B, that I argued like that way. So, the fluorescence intensity in presence of quencher, which is typically denoted by I can write this I as 1 over 1 plus K d, right, this transformer quenching constant for this. So, let me write K d A into Q, the initial intensity I 0 A, right. Remember I 0 by I equal to 1 plus K d A into Q. So, from here I have written plus I 0 B, because the I 0 B fluorescence unaffected, because quencher cannot reach to that site B site to quench the fluorescence of this fluorophore which is present here, which is marked as B. So, I 0 B will be I 0 B even after you will add the quencher molecule, clear. So, what I can do? I can take the ratio of I 0 by I as usual. I 0 by I is equal to I 0 A plus I 0 B into 1 plus K d A into Q divided by I 0 A plus I 0 B into multiplied by 1 plus K d A into Q. Now, what I intend to do? I intend to plot I 0 by I versus Q. Obviously, this is a complicated, right, thing, and if you plot this I 0 by I versus Q, let me plot it somewhere here. So, this is my I 0 by I versus Q. What you will see that the curve will look something like this. The curve will look something like this. It means that this is not a straight line. Obviously, it is not. So, in this case, my question is how I am going to calculate what is the value of K d A. Right. Let us move forward and see how can we do that. Let us write this I equal to I 0 A by 1 plus K d A into Q plus I 0 B, that is what I was writing, and let me write this quantity I 0 minus I like. So, what is I 0? Right here I 0 equal to I 0 A plus I 0 B, right. So, I 0 minus I can write it as I 0 A plus I 0 B and then minus I 0 A divided by 1 plus K d A. I do not have any K d B because that fluorophore present in that B site, buried site, is not accessible to the quencher, into Q minus I 0 B. So, this is equal to I 0 A to 1 minus 1 over 1 plus k dA into q. Okay. This is equal to I 0 A to 1 plus k dA into q minus 1 divided by 1 plus k dA into q. This is equal to I 0 A k dA into q divided by 1 plus k dA into q. So, this one I write as delta I. I can also write this as a delta I. So, 1 over delta I is equal to 1 plus k dA into q divided by I 0 A k dA into q. Now, I multiply both sides by I 0 by I 0. I will get I 0 by delta I is equal to I 0 1 plus k dA into q divided by I 0 A k dA into q. So, if you just simplify this and proceed, what you will get is I 0 A plus rearranging, after rearranging I 0 B divided by I 0 A k dA into q plus I 0 A plus I 0 B k dA into q divided by I 0 A k dA into q. Let us assume that f A, this fraction, is equal to I 0 A divided by I 0 A plus I 0 B. Then this equation will change to, so I 0 by delta I, this equation will be equal to 1 over f A k dA to q plus 1 over f A. Remember that f A is equal to I 0 A divided by I 0 A plus I 0 B. Now, you see we got this equation. Now, if I plot, instead of plotting I 0 by I, now I am plotting I 0 by delta I as a function of 1 over q. If I plot, I will get a straight line, right, where the slope will be equal to 1 over f A to k dA, and the intercept will be equal to 1 over f A. So, like this I will be able to calculate what is the value of k dA. Okay. Now, the question is that, as I said, that in this particular case this position is completely buried position, it is not accessible at all, right. Now, if both are partially accessible, so in this case my equation will be anyway. So, I 0 is equal to I0A plus I0B, but in this case I will be equal to I0A divided by 1 plus KdA into Q plus I0B divided by 1 plus K dB. It is for the side B. So, I have written K dB. In this case what I am telling? In this case both the sides are accessible, but not at same extent, right. So, the transformer quenching constant may be different for the different side, although the same molecule. Here my condition is the quencher is the same molecule, it is also interacting with the site A, it is also interacting with the site B, the fluorophore which is present in site A and site B, they are also same, but their accessibility is little bit different, right, and that is why all these differences are coming. The first case what I showed is that the one is fully accessible, another is 0 accessibility, that is completely inaccessible to that quencher, but here I said that is somewhat accessible. Okay, so then this will be equal to Q. So, now if I just write this ratio I by I0, what will happen? I will simply get, you can just see later on, this will be equal to I0A plus I0B into 1 over 1 plus KdA into Q plus I0B divided by I0A plus I0B to 1 over 1 plus KdB, that KdB will come over here into Q. So, this I will write as FA, that is what I have defined like this way. Here you see FA. So, FB, oh, so this should be small a, anyway it does not matter, FA, FB, same thing. So, I0B divided by I0A plus I0B is defined like this way. So, this is FA to 1 by 1 plus KdA to Q plus FB to 1 by 1 plus KdB into Q. So, for having more than one side, more than two sides, so I will just simply write the sum is Fi divided by 1 plus K di into Q. So, this is going to be little complicated. So, and the one of the limiting thing is little easier, but let us proceed with this. Let me show you the emission spectra of that what I showed you earlier, that protein having 2 fluorophore. It is the same diagram, let me draw over here, that is what that one, right, that is the same thing. Now, I have one over here, as I said I have one over here, and this protein having these 2 fluorophore present in 2 different location, and consider that for this fluorophore mu E is greater than mu G, and this whole protein is present inside water buffer, right. So, outside there is a buffer. So, this fluorophore is accessible to buffer more compared to this fluorophore. Excited state double moment is more than crowd state double moment. You remember the solvatochromism of a fluorescence. So, the fluorescence of this one will be red shifted compared to this one. Let me write that, red shifted fluorescence. This will be blue shifted fluorescence. So, if you take this fluorescence spectra of this, what you will going to see is fluorescence spectra, emission spectra, right, intensity versus wavelength. See, there is something over here, probably you are going to see such kind of thing. Looks like there is something over here, right, because one is little red shifted, another is little blue shifted. So, in this case, this part of fluorescence is given by this fluorophore, and this part of the fluorescence, because this is a red shift, higher longer wavelength, lower energy, this part of the fluorescence is given by this fluorophore. As I said that one of them is accessible, more accessible compared to the other. That means, this fluorescence intensity, that this I by I0, that is what I just have calculated, this is a function of wavelength. If I calculate at this wavelength, then this I by I0 value, and if I calculate at this wavelength, then the I by I0 value will be different. Certainly it will be, because when I will calculate the I by I0 for this wavelength, then there will be lot of change in the fluorescence intensity. When I will calculate the I by I0 at this wavelength, then there will be less change in the flow. So, here is a less change, here is a more change in the fluorescence intensity. So, these are the function of lambda. Okay. So, this function of lambda, then that summation what I have written, this a phi, that also has to be function of lambda, because at this particular wavelength the contribution of this one and this one is something different than at this wavelength, because the emission spectra shifted for the location A and location B. Remember, here this is my location A and this is my location B. So, emission spectra is shifted. If the emission spectra same, exactly same for the location A and location B, then I will not have such kind of wavelength dependency, and this Fi is also the wavelength independent. But in this case, as there is a change, so I have this Fi is a function, it depends on the wavelength. So, then this divided by 1 plus k d I lambda into q. So, I can write this k d I lambda, right. This k d I lambda, whether it should be depends on the wavelength or not, that is my question. Whether this k d I means for the ith one, it could be A, it can be B, if you have multiple, then C, D and so on and so forth. So, whether for a particular site, either is k d A or k d B, does it depends on the wavelength? Obviously no. So, I should write this only k d I. This k d I lambda, right, it does not depend on the wavelength, because it is a Sternheimer quenching constant. So, it will not going to depends on the wavelength. It is the interaction between the fluorophore and the quencher, right. So, the where that molecule will emit, I mean it does not matter for it. Okay. So, ultimately what we will going to have this I lambda by I 0 lambda is equal to sum over I f I lambda by 1 plus k d I into q. Like if I have 3 such different sites, then I can simply write I lambda by I 0 lambda equal to f 1, that is for my first site, divided by 1 plus k d 1 to q plus f 2 1 plus k d 2 to q plus f 3 1 plus k d 3 into q. Now, if I lambda denotes my excitation is emission spectra, right. Emission spectrum. This I lambda has the component of 3 different species. In this case, you see, this is for the F1, F2 and F3, right. So, this I lambda, if I multiply it by F I lambda, that will going to give me intensity for the ith site at this particular lambda. I will simply get that one, right. So, obviously, this I lambda is a measured quantity, right. I will get this one, this is my I lambda. It has the component of B and it has component of A. So, I have measured it together. And now, this F I is that fractional fluorescence intensity, right, for this ith component, and I will get this I lambda, right. So, if I analyze, let us say for example, if I analyze this thing in a global fitting method, then what you will get? You will get the global fitting method means that same equation will be applied for all different wavelengths. Note it down. This contribution F1, F2, F3, they are wavelength dependent, I by I 0 wavelength dependent, but KD2 or KD1 or KD3 they are not wavelength dependent. So, for each wavelength, if you plot I by I 0 and then just fit this one, right. So, you will get the unique value of KD1, KD2, KD3. So, you will get unique values of KD1, KD2, KD3 and also all the Fi lambdas at each wavelength. Fi lambdas at, okay, so Fi lambda means at each wavelength. Okay. And what I know, another information is Fi, sum over I Fi is equal to 1, that I know. That means, what you will going to get is all this Fi lambda, right. You will get all this Fi lambda and this is your measured spectrum. So, if you multiply this measured one with all this Fi lambda, you will get the spectrum for the ith species, and that is what we call this as quenching resolved emission. Spectra. Okay, so let us stop here and we will continue on the next day. Thank you very much.